Hello, ladies and gentlemen, and welcome back to problem number 3 on our 2017-2018 year Alberta High School Contest Part 2. So problem 3, just a single line. What have we got here? Prove that the numbers 26 to the power of n and 26 to the n plus 2 to the n have the same number of digits for any non-negative integer n. Ooh, okay. So, things that we might start thinking about, I'm seeing exponents here. And talking about the same number of digits, we might start thinking logarithms. That's certainly a possibility. Because, for example, if you take the log base 10 of a number, and you take the floor function of that, and I believe add 1, that should be the number of digits in your number. Okay? So there's certainly sort of that idea, that option. We might resort to logarithms, but I don't think so. It's sort of a later concept in high school. Let's see if we can get around it another way. Okay. We'll get rid of the last question. 26 to the n. Now, 26 is kind of unusual. We might think, why 26? Why bother with 26? Okay, would this work with 25, 27? Is there something about 26? It's a semi-prime. It's 2 times something. So I suppose we could point out that you could factor out 2 to the n and you're left with 13 to the n. 13's a prime. So that might be interesting or useful. Now, in terms of having the same number of digits, okay, what's the best way to say it? So I don't quite know how many digits 2 to the n has or 26 to the n, but how would you get digits? Well, if they don't have the same number of digits, then we can see, since 26 to the n plus 2 to the n is the greater of them, then 26 to the n plus 2 to the n will have more digits. Can we conclusively say something like it's got to be exactly 1 more digit? Or maybe, there's some expression in terms of n as to how many more digits it would have to be. So that's something to think about. Now they want us to show that this can't happen. Okay, that's sort of our task. So we know that 26n plus 2 to the n would have to have more digits. Now, just thinking about this, 26 and 26 plus 2, which would be 28, that's the same number of digits, 576. It's 676 is 26 squared. And then if I add on 4 680s, we're not really getting close, but I have to believe that if you raise 26 to some power, eventually it'll get close to 9 something or other. And then maybe adding 2 to the n allows you to sort of tick over and get into the ones. So you sort of gain a digit by adding. And they want us to show that that doesn't happen. So I guess what they're trying to say is, I don't know what power of 10 it would be, but so another way to say that they have the same number of digits is we must show that for any k, (26) the n, you can't have, so this situation is impossible. Or yes, technically it can be greater than or equal. Because this is the smallest number that has k plus 1 digits. Okay, and so if we've got k digits for our 26 to the n, however many digits that is, and if we've got more digits here, then we'll have at least k plus 1 digits. So it's got the 26 to the n plus 2 to the n has to be at least 10 to the k. So this is a good idea, but we have introduced another variable, this k here. Is there a way to deal with this? Well, everything here is even, so I could take out a factor of... You take out a factor of 2 to the n over here. You take out a factor of 2 to the n here. So these two are consecutive multiples of 2 to the n. So we should probably point that out. Okay, so if this doesn't happen, if there isn't this 10 to the k in here, then we've got to... Well, I suppose... So we want to show there can't be a 10 to the k in there. So one thing we might want to at least show is that this expression here can't be 10 to the k. Oh. So 10 is less than 26. So it follows that 10 to the n is less than 26 to the n. And if that's less than 10 to the k, then n is less than k. So 10 to the k is also a multiple of 2 to the n. Specifically, 10 to the k is 2 to the n times 2 to the k minus n, because n is less than k, and then 5 to the k. Okay. So we could put that together with the 2 to the n sort of comment. So since 26 to the n, 26 to the n plus 2 to the n are consecutive multiples of 2 to the n. But 10 to the k is a multiple of 2 to the n. Then in order for this scenario that we don't want to happen, in order for that to happen, we must have 10 to the k is equal to 26 to the n plus 2 to the n. Okay? And so now what I'd like to do is show that that can't happen. Okay? So if we can show that this is impossible, then we have shown 26 to the n and 26 to the n plus 2 to the n have the same number of digits. Okay. So what do we do? How can we handle this? I'm going to say something like let k equal n plus m. Here, m must be positive. Okay, so 10 to the k is really 10 to the n plus m. So we can say 2 to the n, 5 to the n, 2 to the m, 5 to the m. Okay. So I can cancel out the 2 to the n's. So we're left with an even number times a power of 5. 13 to the n plus 1. Is this doable? How could we approach this? We could try looking at it mod 13. We need to sort of show that this can't happen is our goal. So obviously 13 to the n is definitely odd. And 1 is odd, so if you add those up, it's even. Well, this thing over here is even as well. But, what if we worked... So what if it was... If m is at least 2? Now I'm thinking about last digits. So I'm wondering, can 13 to the n ever end in 9, 9? Because if it could, then adding 1 might end in 0, 0. But if this is impossible, then 13 to the n plus 1 will never end in 0, 0. And then if you've got at least 2 2s and at least 2 5s, this will end in 0, 0. So that's my current thought here. Now 13 to the n ends with 69, and this is not going to be pleasant to work out, because remember, we can't use calculators here, so perhaps this isn't the best way to go about doing the question. I think that might not be the best approach. That's okay. Well, maybe working mod 13 wouldn't be such a bad idea. So this here, it's 5 to the n, and then 10 to the m, 13 to the n plus 1. Now 13 to the n plus 1 is congruent to 1. Mod 13. 2, so powers of 2, mod 13. We should run through just about everything. 2, 4, 8, 16, it goes to 3, then 6, then 12. Powers of 5. No, because they're all relatively prime to 13, so I don't think that's going to help. So modulo 13 isn't necessarily the best way to approach this. I don't think this should, like, obviously this can't be true, otherwise what they're asking for is impossible. Well, maybe dividing by 2 to the n isn't the best step. Although it just seems so natural to do that. Hmm. There really isn't anything else in the question that can help us. It was just a nice single statement. So if we look at this modulo 10, that turns into 0, 6 to the n, 2 to the n. But of course, 6 to the n, no matter how many times you multiply 6, it's always going to end in 6. So this is really 6 plus 2 to the n, and powers of 2 end in 4 whenever n is congruent to 2 mod 4. So for 2 or 6 or something like that. But that doesn't mean that this can't happen. So maybe modular arithmetic isn't the way to go on this question here. I worry that there's something simple that I'm missing. Why can't a power of 10 be a power of 26 plus a power of 2? Why can't a power of 5 times a power of 10 equal a power of 13 plus 1? So this thing here ends in m zeros. I would need this to end in m zeros, so 13 to the n must end in m nines. And then adding the 1 carries everything over. Or we could try and keep all the n's together. Say something like 10 to the m must be 13 to the n plus 1 all over 5 to the n. But I don't really see how that's going to work. I mean, you could try and mth root everything. But I don't have enough of a handle on this expression here. I mean, I know that this would have to be less than this expression here. But again, there's no reason to think that it, I mean, if I were able to show that this has to be less than 10, or even less than or equal to 10, we'd be all set, but there's no sort of evidence for such a relationship like that. And I've also got it wrong, and the inequality should be the other way. This is bigger than or equal, well, this is definitely bigger than the mth root of 10 to the n over 5 to the n. Bigger than the mth root of 2 to the n. But we don't really have a concrete relationship between m and n. We know m has to be positive, but no one said anything like n has to be bigger than m or something like that, right? I don't know. Let's just play around. 13 and 13 ends with 69, which is technically minus 31 if we're working mod 100. Times 13, it'll be 93, 10, so it'll be just a plain old ordinary minus 3. So it'll be 97 times another 13 will be minus 39, which would be 61. What we don't want to see is 99 when we do this. That's all. And there's going to be... So it'll never end with a 5. It'll only end with odd numbers. But it could conceivably hit every number. 3, 8, and then the 100 no one cares about, and then 0, 1. So 93. That's minus 7, so that's minus 91. Which should just be 9. 9 times 13. Will be 27 plus 90. So 17. Is there a chance we miss? For example, the reason I'm doing this, if you take a look at powers of 7, they end with 0, 7, 4, 9, 4, 3, and then they go to 0, 1, and they repeat. So if there's a nice repeat here with 13, if we hit 0, 1 before we hit 9, 9, then we'll be able to conclusively show that, okay, this thing here can't end in 2 zeros, and that would mean m has to specifically just be 2, or it has to specifically be 1, and we could maybe work with that. We could maybe rule out 1 as a possibility because 26 is growing really, really fast. So this should be 221, so just 21 times 13, you'll get 63, 10, so 73. It'll be a lot easier if we had a calculator. Okay, 73 times 13. 9, 21, no one cares about the 2, and then the 30. So 49, that's another one. I definitely think there probably has to be a better approach than this. But I can't currently think of one off the top of my head, which is a little disappointing. So 87 is minus 13, so we should get minus 69, so that should be 31. 31 times 13 was just 3. 3 times 13 was 39. And we should get 17. And 93. So it should go to 7. Hold on, I had 17 over here. Why am I getting minus 17 here? So 87 times 13. 87 is minus 13. So 21 and then 240. And then 70, so I get the 1. No, 31 was right. (31 times 13 ends in a 3. So basically, we're just going minus negative of each of these mod 100. So 39, and then it should be 17 again. But I thought we already hit 17. So 9 times 13, 7. Carry the 2. Just get 2. 0, 9. 7. And carry the 1. Yeah, it should be 17. This is quite bizarre. (39 times 13). Let's try that again. 7, carry the 2. 1, 1. 0, 9, 3. 7, 0. Ah. There's our problem. We never actually hit 83. This was me multiplying things out. I should really keep better track of things. Okay, so from 39 we go to 7. And it looks like we go to 91. And then 91 we would go to 83. And then minus 21, which would be 79. We'll do a quick spot check. 83 times 13. That's 79. So from minus 21 to minus 73, so that'd be 27. 49, which would be 51. I'll do another random spot check. 81, and then 7. 5, 1, yeah. Then that went to 37. Which is minus 63, so 63. And then 63 times 13. Get us 9, 8. Oh, no, that's... Oh, did I make a mistake? Yeah, 111. This should be 81. Oh, good. Well, I was wondering what was about to go wrong because we'd never gotten back to 1. We were about to cycle around to 13. So, that was a whole giant waste. 81 times 13, we get 243, and then the 10, so 53. We'll just skip over that and go to 53 times 13, and 9, 5, 3, so 89. So that's negative 11. So we should get negative 43, so that should be 57. $57 times 13 is something. 1, 2, so that should be 7. So we get 41. 41 times 13, so that'll be 123 plus the 10, so that'll be 33. 33 times 13. 99 plus 30, so that should be 29. 29 times 13, 7, carry the 2, 8, and then 9. That'll be 77. Times 13, we should get 1, carry the 2, so that'd be 31. 70. And we get back to 0, 1. There we go. Okay? We never have 13 to the n end in 99. So what can we conclude? M would have to be 1. So what we're really looking at is 10 to the n plus 1 is 26 to the n plus 2 to the n. That's what we must have. And this seems a tad ridiculous. You probably make a quick little chart. But 10 to the n plus 1 should be easily outpaced. 100, 1,000, 10,000. 26 to the n. 26, yeah, that's fine. 676, okay, but then we should be getting more than 10,000 when we do the next one. And we'll just quickly, again, multiply out by hand. We see 26 to the n is greater than 10 to the n plus 1. For n greater than or equal to 3. So n would have to be 1 or 2, and we can see 26 plus 2 is not equal to 100. And 676. I don't know why I keep writing 576. I'm just more used to powers of 24, I guess. Plus 4 is 680, which is not 1,000. So our conclusion is 26 to the n plus 2 to the n has the same number of digits as 26 to the n. I can't think of a nicer way. There probably is, and you're more than welcome to read their solutions. A nicer way of doing it, but let's just quickly sort of review what we were talking about. Okay, so we know that if they're going to have a different number of digits, then they have to be on either side of a power of 10. And then we just sort of started narrowing down what this power of 10 could look like. It's got to be greater than 10 to the n. That's pretty quickly noticeable. And then because these are consecutive powers of 2 to the n, it follows that the only way for this to match up is for our power of 10 to actually be 26 to the n plus 2 to the n. Otherwise, you have a power of 2 to the n between two consecutive ones, and that doesn't make any sense. So this equality here has to be the only case. And then it took a little while, sort of rearranging to look like this, and we see that this was just experimental. But we sort of worked them all out. It wasn't that many, but it was a little annoying, and the very easy arithmetic mistakes. I mean, I made one here. For all I know, I made another one, and this method doesn't work, but I'll double check before I post it. But then we were able to just sort of, by working modulo 100, show that you get back to 0, 1 without hitting 99, and so powers of 13 will never end in 2 nines. So how could 13 to the n end in m nines in order for 13 to the n plus 1 to end in m zeros? Can't work. So since you can't have 9, 9, but you obviously can have it end in 9, we then say, okay, well, m equals 1 is a special case, but that gives us a single equation just in n, very, very quick, with a nice little chart to rule that out, because 26 grows so quickly. Okay? So I'm happy with it. I'm going to, obviously, before I upload, double check that the modular arithmetic all worked out, but I'll leave that out because I think this has gone on long enough, and I will see you in the next video for problem number 4. Take care.